Hello everybody, welcome to our class session on definite integrals. Today we enter a totally new area, definite integrals. It is a third great idea in calculus. What are the other two again? Well, think about it. Number 1, limits. Number 2, derivative based on the concept of limits. And number 3, definite integrals. Now you might wonder why definite integrals could be so new. Didn't we discuss indefinite integrals or antiderivatives already? Well, the truth is that definite integrals and antiderivatives or indefinite integrals have, on the surface, very little in common. We will later see, in the Fundamental Theorem of Calculus, that they are very closely related, but on the surface they are not. Antiderivatives are really just the opposite of derivatives, so I don't think the idea is really new. That's also why I prefer to call them antiderivatives and not indefinite integrals. They are just the backside of the derivatives coin. Let's give the motivation for the idea first. Computing area and volume was a very urgent and practical problem in every evolving civilization. Now Mesopotamia, ancient Egypt, ancient India, to name just a few, did have formulas for areas of rectangles and triangles. Some of them also had formulas for volumes of prisms and pyramids. This was essentially the state of the art around 250 BC. The question of the area of a circle of radius r was also rather important, and every early civilization did approach the question. However, the answers given were good, but certainly improvable. In Mesopotamia, the formula used was a equals 3r squared, later improved to a equals 25 over 8r squared, which is about 3.125r squared. And Egypt used already around 1650 BC the formula a equals 16r over 9, the whole thing squared, which is about 256 over 81r squared, which is about 3.160r squared, relatively close to the formula we use today. Now enters our hero for today, Archimedes of Syracuse, living from 287 to 212 BC. He is well known for the Eureka. Archimedes' approximation for the area of the circle was a equals 22 over 7r squared, which is about 3.143r squared. Rather close to the true value of pi. Remember, pi is 3.141593. Now the point here is not the fact that this is the best approximation for pi found so far. The point is that Archimedes used a method that would have allowed him, if he would have desired so, to find better and better approximations, as close as he wanted to do it. The method, an early version of our great idea, is a so-called exhaustion method. To be fair, the method has gradually been developed by others, most notably probably Eudoxus. Let me illustrate the exhaustion method used by Archimedes at a circle. For simplicity, look at a circle with radius r equals 1. We can inscribe a square with base length square root of 2. Therefore, the area of such a circle would exceed the area of the square, which is the square root of 2 squared, or 2. Next, we inscribe 8 triangles, as shown here. Each one has an area of about 0.353. Thus, the sum of the areas of those 8 triangles is about 8 times 0.353, which is about 2.828. Since these triangles are inscribed, we know that pi must be at least that large. We can proceed like this, fill the circle with any number of triangles. Here are the calculations in a simple Excel sheet. You can see that the numbers will go very close to pi. Well, the limit of these numbers will be pi. Of course, one would also have to argue why the waist, not covered by the triangles, approaches 0 as the slices get thinner and thinner. Another famous application of the exhaustion method used by Archimedes was to the parabola. Assume we want to calculate the area colored. Archimedes puts in one triangle of width 4, height 4, and therefore area of 1/2 times 4 times 4, which is equal to 8. Then he draws two triangles. They have area 1 each. Then these four triangles of area 1 over 8 each. Adding up all these values and going to the limit, we get a value of 10 2/3. Actually, Archimedes did show something more general, and I didn't show the details here. The subject might be worth its own video. So why don't we give Archimedes credit for inventing calculus? Because he didn't. The Greeks did not have a notion of the first idea, limits, and they didn't look at the derivatives. And even with the third idea, they went only halfways. The exhaustion method, as used by Archimedes, worked in some cases, but not in others. It certainly wasn't the general method yet. The general method was developed about 2000 years later by the mathematicians Pierre de Fermat and John Wallis, and also put in a more general framework by Newton and Leibniz again.